In this video, we'll be continuing our exploration of the Titanic dataset. And the exciting thing in this video is that we're going to be going deeper into the machine learning concepts beyond the regressions and the basic data analysis we did in the last two videos. So we're going to be using in this video one of the more simple machine learning techniques called KNearest Neighbor. And how that kind of works at a visual level is that we're going to have some similarity measure between each two passengers. So let's say I'm passenger I and you're passenger J. So we're going to have some number called S subscript ij, which is between 0 and 1, which tells us how similar we are as passengers. So if it's close to 0, that means we're not very similar. If it's very close to 1, that means we're very, very similar as passengers. So let's say for a second, and we'll be constructing the function which tells us a similarity, but let's say for a second we have that function already. So we have the numerical similarities between each two passengers. So given that, let's say now we want to find out if passenger I survived the Titanic disaster or not. So we can look at this kind of graphically. Let's say that passenger I is this represented by this dot right here. So now, out of all the other n passengers on the Titanic, or out of the other n passengers, or I guess n-1 passengers we're looking at in the data set, they're going to have we're going to look at the ones that are closest to this passenger. So if this is passenger I, let's say graphically the other passengers lie like this. So let's say this is another passenger, this is another passenger, this is another passenger, and so on. And the distances represent what's the similarity between them. So the closest ones actually have a similarity close to 1, and the ones that are all the way out here have a similarity very close to 0. They're not very similar to this passenger. Now the k in KNearest Neighbor is user-defined. We can define it as whatever we want, and that just tells us how many neighbors we're going to be looking at. Let's say for the sake of this simple example, we're just looking at 3 neighbors. So we're going to look at the 3 nearest neighbors to this person I right here. So it looks like that's this person, it looks like it's this person, and maybe it is this person. So these are the 3 nearest neighbors to person I. Now what we look at is what's the status of these 3 people. Let's say this person survived the disaster. Let's say this person did not survive, so we'll put N, and this person survived. Since 2 out of the 3 survived, we're going to estimate, we're going to guess that person I also survived, because 2 out of the 3 neighbors survived. It's likely that this person also survived, and the rationale behind that is since this person is similar to these other 3 people, these are the most similar people to this person, we're going to say that his or her fate was also similar to the fate of these other 3 people. So that's kind of the rationale behind it, and logically it does make sense. But again, one of the caveats is that k is user-defined, which means that if we looked at a different if we took a different k, we might get different results. For example, let's say instead of k equals 3, we looked at k equals 5. So now we're looking at the 5 nearest neighbors. So maybe we're looking at this person as well. Maybe we're looking at this person as well. And let's say for these two people, these people did not survive. So now we've changed the outcome because now we have 3 non-survivors versus 2 survivors. So we'll say this person did not survive. So the best thing, one of the better things you can do is if we have a lot of people, then we can pick k kind of big so that we get a better sample than just 3 people. And also some kind of strategy you can use is let k be odd so that there's never a tie, because we're just looking at bivariate cases. There can be, if there's a tie, it's kind of unclear what to do. So we'll be keeping k as odd in all of these cases. So I'll let you know the exact value of k we use a little bit later in the video, but right now let's see how we construct this similarity measures. So this W is called a similarity matrix. It's an n by n matrix, so it's n is the height and n is the width. And n can be everyone in the sample, or it can be a subsample of the people. And the reason we wouldn't choose everybody is that this k-nearest neighbor, it grows quadratically with the number of people you choose. For example, if you double the number of people that you're using in the sample, then the number of computations is going to quadruple, because you're going to have doubling the height, doubling the width, so it's going to be times 4. So that's one drawback of this right away, is that it's order n squared, so it takes n squared time to run versus some of the other methods we might have used before. So we're going to be using just an arbitrary n, maybe it's the whole sample, maybe it's some subset, whatever. Now what do you do? So this W is the similarity matrix. This tells you the similarity between the first person and himself. This tells you the similarity between the first person and the second person. This is the similarity between the second person and the first person, and so on. So Sij, so Sij, as we said right here, represents a numerical similarity between 0 and 1 between the ith and the jth person. Let's observe some things about this matrix before we determine exactly how to calculate these similarity measures right here. What is S11? What should it be kind of logically? What's the similarity between a person and him or herself? It should be 1, right? Because you can't get any more similar than having a copy of yourself. So that means this should be 1. Also, for the same reason, S22 should be 1. For all these S and N should be 1. So this diagonal should be full 1s. Now, what's S12? Well, it could be anything. The second person could be any similarity with the first person. But whatever it is, what should S21 be? So what's the similarity of the first person and the second person versus the similarity of the second person and the first person? They should be the same, right? Because it doesn't matter what order you take them in. They should have the same similarity. So in addition to having 1s on the diagonal, this W matrix, the similarity matrix, is also symmetric because this is the same as this is the same as this, and just like that, every component, Sij, basically equals Sji. That's what symmetric matrices mean. So that's kind of all there is to know about the similarity matrix. It's a matrix of the similarity measures between each group of people. It's symmetric and it has 1s on the diagonal. So now let's get to the meat of what we're talking about. How do we determine the similarity between two people? Well, let's start with this. We're going to go about it iteratively so we can kind of build on previous knowledge. We're going to go ahead and look at 3 characteristics of people to kind of keep things a little bit simple for right now and kind of taking inspiration from the regression cases we were looking at before. We're going to be looking at someone's sex, their fair, and their age. So that's kind of like a triple, so we can represent it as a vector. So let's say for person I, let's say Vi is a vector which has their sex, their age, and their fare that they paid to be on the Titanic. Now similarly for Vj is the same set of values for person J. It's their sex, their age, and their fare. Now, what's one of the most crude things we can do to figure out how similar these people are? We can subtract these 2 vectors, right? So let's just do that. Let's say we do Vi minus Vj, and then we get another vector, another triple, which represents the difference between their values. So we have Si minus Sj, Ai minus Aj, Fi minus Fj. And we see that if each of these is small, that means that Si is similar to Sj, Ai is similar to Aj, Fi is similar to Fj. Then if each of these is small, then we can say these people are pretty similar because they have similar sex, similar age, they paid a similar amount to be on the Titanic, similar fares, right? So we can go ahead and say that. But let's do a little fix right here because we don't want the order to matter because we don't want this, if we took Vj minus Vi, then this would be negative rather than positive if it was positive in this case. So we don't want the order to matter. So when we're compressing all this down to a single number, rather than just adding up these 3 components, we're going to be adding up their squares. So what we're going to be doing is, let me do this in a different color. We're going to be doing Si minus Sj squared plus Ai minus Aj squared plus Fi minus Fj squared. And then we can take the square root to kind of get it back into the units we were working in before. And this is known as, you probably know it as the norm of a vector, the Euclidean or L2 norm. So that's written as Vi minus Vj with a subscript 2. You can write the subscript 2. Most people, if you don't put the subscript 2, they'll just know it as the norm. But again, there's the L1 norm and the L2 norm. So just to make it clear, this is the L2 norm. So to be clear, what we're doing here is we're taking the subtraction of the sexes. Remember, sex 1 is female, 0 is male. We're taking the subtraction of their sexes, squaring that, subtraction of their ages, squaring it, subtraction of their fares, squaring it, taking the square root. And the squaring is just so the order doesn't matter, so the negatives don't really matter. And we have a nice value right here. Now, we still have a little bit of a ways to go because the one initial issue here is that the magnitudes of these things are pretty different. Let me show you what I mean. So let's say one person is male and one person is female. That means we'll have a 1 minus 0 or 0 minus 1, whatever. In the end, this is going to be 1 squared, which is equal to 1. So it's going to contribute that much to the difference. Now, that's actually a huge difference because that's the biggest difference you can have in sex. You can't get any bigger of a difference than that. So this should be actually a big deal. Now, is it a big deal compared to these other components? Let's look at fare. So, for example, if someone paid, let's say, $18 to be on the Titanic and someone else paid, let's say, $22 to be on the Titanic, that's not a big difference when you look at the range of values that people actually paid. There's some as high as 512. There's some pretty high values. So, but if we take the subtraction of these two, we get 4, and we square that, and that becomes 16. That's huge in comparison to this one. That pales in comparison. That's gigantic in comparison to this one. This one is very small. So this one kind of gets swamped by this, which is not very big deal. So we kind of want to, in a way, normalize all these values so that they kind of have the same pull, the same impact on the overall difference between people. So how are we going to do that? We're going to actually, you can do many different things. You can kind of use whatever method you want that you think will kind of get them the same units. For example, one that we're not going to use, but which we'll mention, is that you can take instead of taking age I and age j, you can take AI as the age of a person minus the minimum of all the ages divided by the maximum of the ages over min ages. So let me write that in a formula. So instead of taking AI, let's say you can take mi, which is the modified age. So you can take modified age I is equal to the age of a person minus the min of the ages over the max of the ages minus the min of the ages. So this kind of normalizes because this is going to be a number between 0 and 1, right? Because you can't have age I be any bigger than max of the ages. So this is going to be between 0 and 1, which kind of brings into the same ballpark as the sexes, which are between 0 and 1. So we can do that, but what we're going to do is we're quite literally going to normalize. So we're going to do the normalization metric, which involves, so if you normalize something, let's just say ni is equal to, if you take the value, so we're going to do age I minus the mean of the ages over the standard deviation of the ages. So you might have seen this in your stats class. If not, it's just a way to get the mean of all your ni's to 0 and the standard deviation of all your ni's to be equal to 1. So now this kind of really only works if the data you're looking at is already normal. And normal means that it kind of looks like a normal distribution or very close to normal distribution like that. So let's look at how do the ages look. So we're going to go ahead and look at a plot of the ages right now. So here it is.
From this histogram of the ages, we see the ages look pretty normally distributed. They look pretty close to a normal distribution. So we're qualified, we're validated in using our standardization metric from the previous page. Now let's compare that with the fares instead. If we look at a histogram of the fares shown here, it looks kind of like the right half of a normal distribution, or it has a long tail going in the right-hand direction. So right away it doesn't seem like we're qualified in using the standardization metric because it doesn't really look like a normal distribution. Now there's a little trick we can do. When we have a distribution like this, where we have a tail going off in the right direction and high values up front, we can take the natural log of it to get something that looks more normal. So let's go ahead and do that. And when we take the natural log of these fare values, we get a histogram which looks like this. So this is now natural log fare versus frequency. So this looks more normal. Maybe we're more qualified using this in our standardization metrics, so taking the normalized of the natural log fares instead of just fares. So that's what we'll do. So now let's return to the previous work and using these transform metric.
So now that we did all those data transformations, we have quite a different metric set than we had before. So remember before, on the back of the page, we were defining VI as someone's a triple of their sex, their age, and their fare. Now, since we had to do those data transformations to kind of get things in the same ballpark and make sure each thing had a similar impact, right now, currently what we're looking at is that VI is now defined as sex didn't change, that's still SI. Now, instead of age, we're looking at normalized age, so we'll put as NA. The normalized age of the ith person, and instead of fare, we're looking at normalized natural log of fare. So we're looking at normalized natural log of fare of the ith person. So this is now our triple, and similarly for VJ, it'll be all the analogs with the jth person. So now, does that work? So if we take these values instead of the previous values and we put them into this metric, is that better? In a sense, it is a little bit better because we now have things kind of in the same ballpark as this sex variable. So we have, at least we know that their mean is 0 and their standard deviation is 1, so they're kind of in the same ballpark. But that still doesn't guarantee that they're going to have the same impact. So now the next thing we did to kind of tweak it is something we just did kind of empirically. So what I did was, I'll just write VJ here so we can compare. SJ, NAJ, NLN, FJ. I promise this ugly notation will go away in a little while. But so yeah, we had VI and VJ. So now what I did was I took the subtraction and I did that. So I did VI minus VJ and I took the average of these differences. So I took SI minus SJ and I took the average of that difference over a bunch of different pairs of people in the subsample I was looking at. And I did the same thing for NAI, NAJ, the difference between NA and the difference between NL and F. And I found that the average of the differences for the sexes turned out to be 0.46. the average of the difference for the normalized ages was 1.1, and the average of the difference for the normalized natural logs of the fares was 0.3. So that's okay. That's a little better. At least they're kind of in the same ballpark, but still, we see that this is more than double of this, more than almost triple, or more than triple of this. So the simple thing we can do is kind of just use these empirical values to assign coefficients to each of these differences to kind of put them, make sure their averages are the same or very close to the same. So what I mean by that is instead of doing Si minus Sj, we're going to put a K S multiplied by Si minus Sj. And we're going to have a K A multiplied by AI minus Aj and a Kf multiplied by Fi minus Fj, where K, let's see. So this would be for the ages. So we're going to say Ka is equal to 1 because we're going to baseline everything at 1.1. We're going to say that Ks is equal to 1.1 over 0.46, and we're going to say Kf is equal to 1.1 over 0.3. And the reason I'm doing that, so let's demonstrate with, for example, Ks. So the reason I'm doing Ks as 1.1 over 0.46 is that if we do that, so if we do Ks as 1.1 over 0.46, then that multiplies by Si minus Sj, right? And we saw that Si minus Sj's mean was 0.46. So if we systematically multiply those differences by 1.1 over 0.46, then their average in the end will come out to 1.1. And the same logic applies for the normalized natural log of the fares. That happens since they're systematically, their mean is 0.3. If we systematically multiply them by 1.1 over 0.3, then their mean will come out to the mean of the difference will come out to 1.1. So in the way we've tweaked it. So we've initially tweaked it by making sure that we normalize it, in this case taking the natural log to get in the same ballpark, and now we've done the final tweaking. So now you ask, are we done now? The answer is still no, we're almost done. Let's look at why we're not fully done. So let's write down what we have so far so that we can see where we have to go from there. So we'll write Ks Si minus Sj squared plus K, Ka. This is Nai minus Naj squared. And finally plus Kf. This is N ln Fi minus N ln Fj squared. So this is our current trial metric. Does this live up to the expectations we want? The answer is almost. So the problem with this is that the more similar two people are, which means the closer that their I and j values are for each of these, this will be closer to 0, right? Because if people are very, very, in the most extreme case, if we're looking at the same person with himself or herself, then this is going to be 0, this will be 0, this will be 0, so this entire thing is 0. But we want kind of the opposite. We want the more similar they are, we want it to be 1, because that's going to help us in our calculations later on. So something we can do, very easy thing, this is called it's called the Gaussian Norm, is doing E, the Euler's number, to the negative all of this. Initially you're saying, why am I doing this? That looks really ugly. But why we're doing that is, think about it. So if we have a person with herself, then we're going to have 0 here, 0 here, 0 here. This is 0, negative 0 is still 0, e to the 0 is 1. So we've satisfied that condition where that we wanted, where if we have a person with himself, then they have a similarity of 1. Now, what if we have two people who are very dissimilar? So that we're going to say what that means is that these numbers are very, very big. So this is very big, this is very big, this is very big. Just ignore these coefficients. Let's just say these are very big, so that this entire square root is very, very big. Negative of a very big thing is a very small thing, so very huge in the negative direction. And e to the power of something that is very, very negative is going to be close to 0, right? Because if we look at a graph of the exponential function, e to the x looks like this. So if we're looking at values all the way back here, it's going to be really close to 0, which is what we want. So this is the similarity function we're going to use in the end. So now I would like to really quickly recap everything we did, because I know this was a very iterative process, and it might have lost some of you along the way. I know it can be confusing. And after we finish recapping, we'll give the conclusion, what the results were. So just to recap, we wanted to find a measure of similarity between each two people, each two passengers. And we said our baseline, the things we're going to use to do this are someone's sex, their age, and their fare, how much they paid to be on the Titanic. Now, we said that, okay, we can put each of those in a vector, and we can subtract them. The initial problem here was that we didn't want to do something minus something, because if we flipped it, then we would get a negative here, and we didn't want that to be any different. So instead, we took the square of each of these components, each of these differences, and then we took the square root to get it back in the same units. So our initial guess was that we took the square root of each of these differences squared. Now, we said that the problem with that was that the magnitudes of these were very different, so that if we had a sex difference of 1, that's the biggest you can get. That should be a big deal. But that's kind of swamped if you have even a fair difference of 4, because that ends up having a 16 when you square it. So we said to kind of account for this, we're going to have to normalize our different metrics. So we're going to keep sex where it is because it's already between a 0 and 1 range, but we want to kind of bring the ages and the fairs to that kind of range as well. So the ages, when we looked at the graph, it was already kind of normal. So we were able to use the normalization metric here on it. So we were able to take each age minus the mean of all the ages over the standard deviation of the ages, which guarantees that our new metric, which is normalized age I, will have a mean of 0 and a standard deviation, mean of 0 and a standard deviation of 1. And that kind of helps it move towards the same range that sex is in and have the same kind of impact. Now, we wanted to do a similar thing on the fairs. Now, the problem was when we looked at the fairs, they weren't looking very normal. In fact, they were looking like this. But we said that in the explanation, if something looks like this, if you take the natural log of it, it kind of looks more normal. So we did take the natural log, and then we did the same treatment as we did to ages. We took the normalization metric with fairs instead of ages here. So now we helped each of these metrics right here be in a 0 to 1-ish range. And I'm being kind of fuzzy here because we saw that with these values, they weren't exactly having the same impact. So let's get to that now. So after we did all the transformations here to these two and left the sex as it was, we found that the mean difference of sex was 0.46, the mean difference of normalized ages was 1.1, and the mean difference of normalized natural log fairs was 0.3. We wanted to get these mean differences ideally to be about the same. So we just picked one of them arbitrarily. We said this one. We're going to keep the normalized ages as it is, and we're going to try to move the sex difference and the normalized natural log fairs to move towards that 1.1. How we did that was simply we multiplied the differences in our function here. We multiply the differences by a coefficient, each of them by a coefficient. So since we're keeping the ages where it was, we just left the age coefficient as 1 because we wanted to leave it where it was. And we took the other coefficients and we multiplied by this number divided by, respectively, either of these numbers, so that when we took the mean of those differences, it would go to 1.1 as well. And after we did that, so we had, currently we were here, we took the coefficients. Now we said that if we just had that as it was a bit of a problem, because if we had some person with herself, then their similarity would be 0. If we had people who were very, very different, their similarity would be huge, unbounded actually. So this e to the negative that we just found before helps keeps things bounded between 0 and 1. And it makes sure that people with 1 are exactly similar, people near 0 are very, very, very dissimilar, which is exactly what we want. And this had a name. We can say it was the Gaussian norm. It's often used in the KNearest Neighbor as a similarity function. So this is it. This is our finalized similarity function. Now let's go back to what we said at the beginning of the video. What do we do with this? Now this similarity function is what's used to generate this similarity matrix. So let's say we want to find the similarity between the first person and the second person, which is the same as this. So we take the first person's matrix, which their information vector, which looks like this, and the second person's, which looks like this, and we take each of these components and run it through this formula, and we get a number. And that number is what goes here and here. And that's how we fill in the entire table. Now, let's say we want to try to predict the fate of the first person, right? So how do we do it? So we're going to look at all n of these people in this table. Let's say there's 100 people in this table, so we took a subsample of 100. We're going to look at all 100 of those people, and now I'll tell you the k I used. I used k equals 15. You can experiment with different k's if you want, but I use k equals 15. So we look at which of these 100 numbers, which 15 of these 100 numbers is the biggest. We're going to, of course, exclude this first one, because obviously this one's going to be the biggest because the first person with himself has the biggest similarity, but you don't know the fate of this person, so since you're trying to figure that out, so we're going to exclude the first one. So out of these 99 other numbers, you pick the 15 biggest ones because those are the most similar to the first person. Let's say you have a list of those 15 people, so you have that list. And now you look at the fate of each of those 15 people. So let's say we have survived, blah, blah, blah. Let's say we had 9 survivors out of those 15 people, and we had 6 non-survivors. Since more people survived, we're going to predict that the first person also survived. It's as simple as that. And the beauty of having an odd number is that you can never have a tie. So it's either going to be swaying in the survival direction or the non-survival direction. Okay, so, and you do that for each of the 100 people. You just go through their rows, and it's really nice to be in a matrix. It's really convenient. You go through each of those rows, make sure you exclude themselves because you have no information about them. You're trying to figure that out. And you look at the other 99 people, and you look at the top 15, and you see what their fate was of those people. And you prescribe this person the same fate under the assumption that since they're similar to those other people, they should have a similar fate. So we do exactly that, and the accuracy that we're getting, the accuracy that we get with this is about 76.5%, which is around the same ballpark as what we were getting with our regressions. So we can tell that this method is working; it's doing its job pretty well. So let's talk about a few of the caveats before we end the video. Of course, one of the caveats we already mentioned was that if you double the size of the data set, since if we have 100 people, if you do 200, you're not doubling your work, you're quadrupling your work because this matrix gets 4 times bigger. It gets twice as long, twice as wide, so it gets 4 times bigger. So that will be a strain on your computer when you do all this. Then other thing is that these coefficients are pretty much arbitrary. You can change them to put more emphasis on any of the factors you want. For example, if I made KS like 1000, then sex would be the dominating factor here because these would be very small in comparison to this bigger one. If I made this KS very small, like 0.0001 or even 0, then this pretty much vanishes and it's only about these two. So you want to make sure if you want them to be weighted equally, then you have to kind of do the analysis we did back here. If you purposely want for one of them to be weighted more, then you can go ahead and do that and change your coefficients accordingly. It's just that you have to know what you're doing. You have to know what kind of things are going into here. Also, one of the biggest caveats, and the last one we'll talk about, is the similarity function itself. Nobody says in KNearest Neighbor that you have to use this similarity function here. You can really use whatever you want. We tried to explain one earlier where you can normalize things with this kind of easier norm than the Gaussian, than the this standardization norm we're using here. So there's a lot of things you can define. You can be creative here, and maybe you'll even get higher accuracies if you do things your way. And of course, one of the other things that you're defining is your K. You can have K be as, I chose 15, but what's stopping me from choosing 21 or something like, 45, whatever, or even something smaller than 15, like 7. So it's really up to you. It's a lot of tweaking. That's what I found using KNearest Neighbor. But that's just kind of how machine learning is as you get deeper into it. There's a lot of parameter tweaking. But hopefully you learned something and you're convinced that this method does have a pretty good accuracy, 76.5. That's the same ballpark we were getting before. And it's definitely better than the baseline that we were trying to beat the crude probability. So until next time, we'll go more into machine learning.